So today's physics paper 2022, and the last question is usually a nice one with plenty of choice as well. So I need 2 of 4 here, so I'll have a look at these. Distinguish between a vector and a scalar. So question 14 A. So a vector, well, a scalar first of all is just a number. So mass is equal to 2 kilograms is a scalar. A vector then has 2 quantities associated. It has the magnitude, but also a direction. So speed would be a perfect example of a scalar. So speed would be 20 kilometers an hour, but velocity then has a direction. So a vector then would be velocity, which would be 20 kilometers an hour in the direction of northeast, let's say. So there are the 2 differences there. Label diagram of the apparatus experiment to find the resultant of vectors. Well, that's the one with the Newton meters all clung together, and you have your A, B, and C, and so they all have vectors associated with them. So basically, it's like your star situation there, where you have vectors going out like that, and when they're in equilibrium, then that's the A, and B would be the resultant of A and C, and vice versa. So that's your experiment there to do the resultant of those. So you have basically forces pulling out from the origin in different directions, and once they're in equilibrium, then they are balanced. So it's effectively like one is balancing out the other one. It's almost like that. So object is released with initial velocity 150 meters per second. That's an unusual way to put it. An object is released. Presumably mean a projectile with initial velocity u is 150 meters per second, angle at 20. The horizontal, resolve the velocity in a horizontal and vertical. So for people who do applied maths, this would be fairly basic stuff. So that would be your first step. So that is u cos 20. Of course, it's the basic stuff where you kind of take it for granted and you end up messing it up. So let's keep our eye on the ball. So it's 150 sine 20 in the j direction, and 150 cos 20 in the I direction. Okay, so resolve the velocity in the horizontal and vertical components. So I suppose you do have to, let's throw in the old sine there into the calculator, and let's see what you come up with. So 20 sine 0.342, and cos of 20, what's that, 0.9 0.94, all done by 150, so multiply by 150, so that's 149 or 141, and the other lad is 150 by 0.342, so 51.3. Okay, so we resolve the velocity, the initial magnitude direction of the velocity of the object after 8 seconds given g. Okay, magnitude and direction of velocity. Okay, so that's full scale applied maths problem. So you're at this point here somewhere, it's 8 seconds, and you need your full v vector in terms of magnitude. And okay, so let's get, and it's under acceleration of g, so let's get vx is the easy one, because that's equal to uxt, because there's no force in that direction, it's only straight down. So that's equal to ux, which is this 141, what's in meters per second, is it? Yeah, meters per second. And how many seconds? It's, yeah, so vx is going to be equal to that. What's that? So that's going to be that. So that's meters, yeah, per second. And Vy is going to be the slightly more complicated one, U plus AT. So that's equal to Uy minus GT, which is, okay, Uy, so that's Uy. Let's put a box around that because we're getting marks for that. And that's Ux. Okay, so Uy is 51.3 minus, and we're saying 9.8. 9.8 by 8. Okay, so that's going to be negative because U is going down. It's dropping at that point. So let's have a look at the calculator for that. 9.8 by 8 is 78, and subtract 51.3. So Vy is going to be minus 27.1 meters per second. And Vx equals, that seems very high, the Vx, but I suppose that's fine. It is starting at 150, yeah? Yeah, grand. So Vx is going to be, no. Vx should be equal to Ux. Why am I multiplying it by that? No, it should be Vx is equal to Ux. Vx does not change, so that shouldn't be factored in at all. So Vx is going to be equal to 141. It doesn't change, so that stays at that. Okay, so the velocity in the x direction is constant because there's no acceleration slowing it down. The velocity in the y direction is retarded by this factor AT. Okay, so we now have the vector. Magnitude and direction. Okay, so now we need magnitude and direction. So V is equal to square root of 27, so it's absolute value, so we don't need to worry about the negative, plus 141 squared. And then the direction, we get tan theta. So if it's coming down like this, this is going to be the angle theta. So tan theta is equal to Vy over Vx. So equal to 27.1 over 141. Okay, so let's pop those in. Okay, so 27.1 square that. Okay, so 734 plus 141 squared. So add your 734 and square root it. So 143. So 143 meters per second. Your tan then, okay, 27.1 divided by 141, and then arctan. Okay, so that's, so your tan theta is equal to 0.192. And how do I get the inverse of that? Okay, I'll have to, okay, so the velocity, magnitude of velocity there is that guy, and okay, so the velocity is 143, so it starts out at what, 150. So you expect it to be reduced after a certain period of time because the y velocity is going to be reduced. Your arctan, your tan of that is this. So let's get tan inverse calculator. Okay, and what have we got? Inverse tangent calculator. Okay, so tan inverse of 0.192. Angle in degrees is 10.87. 10.87. Okay, so it will be, you know, Vy is negative, so it'll look like this. So your Vx is the same as it always is. Vx is equal to Ux, and in the same direction. Your Vy is now negative down this way, and this is your theta. So the direction, you're asked for magnitude and direction of the velocity after 8 seconds. So it's 143 meters per second at an angle of 10.87 degrees. And strictly speaking, it would be, that's the angle with the negative vertical direction. So it's, if that's straight down, then that's your 10 or 11 degrees that way. So so that's okay. That's reasonably okay. So that part A is pretty standard. Now, I suppose the one slight thing is that you're bringing in experiments there. And they're bringing in experiments into the non-experiment questions, so that might throw people a little bit. But Doppler effect, they love the Doppler effect. So what is the Doppler effect? So Doppler effect is the increase or decrease of the apparent frequency of a wave due to the velocity of the source. So, and we could probably explain it using a diagram. So this is the wave spreading out of a stationary source. So the frequency is very well determined in all directions. This is if the object is moving, then the frequency gets distorted. So if it's moving in that direction, then the source is moving towards the waves, so the waves are getting closer together, so the apparent frequency increases. And it's always important to have the observer here. So it's because it's the observer, and Einstein always said that everything has to do with the observer. So the observer hears an increased frequency. So that's motion in that direction towards the observer. So the observer hears an increase in frequency because of the bundling of the waves in that direction as it moves that way. The opposite is true if it's moving away from the observer. So if the observer is here, he or she sees waves that are further away from each other. So F dash in that case is lower. Okay, so that's the Doppler effect. And yeah, we've shown the diagram there. Okay, fixed frequency. 5. Yeah.